I'm delighted to be here. Thank you all for coming. So the hidden subtitle in my talk is could machine learn like humans? The hidden subtitle is that currently they don't learn like humans. They learn, but really very much not like humans or animals for that matter. But let me start by saying a little bit about what the type of learning that machines can do today. So most of machine learning today is based on something called supervised running. And supervised running is sort of, some people have characterized this, who want to kind of diss this a little bit, have characterized this as kind of glorified curve fitting, if you want. And so the basic, I'm told there is an impressive pointer here. So the basic idea of supervised running is, for example, you want to train a machine to classify images of cars from airplanes. You show it thousands of images of cars and thousands of images of airplanes. And the machine is basically a parameterized function. So think of it as a panel with adjustable knobs on it, and the position of the knobs determines the input-output function of that system. And so you show it the image of a car, and if it doesn't say car, if it doesn't turn on the red light, in this case, you adjust the parameters so that the output gets closer to the one you want, so that the red light turns on a little bit more. And then you show the image of an airplane, and you do the same for the green light. And so if you do this thousands or perhaps even millions of times with many examples, and every time you adjust the knobs a little bit, eventually they might settle in a configuration where every car and every airplane is correctly recognized, at least the ones that you use for training the system. But the magic, if you want, of machine learning is the fact that the system can interpolate or extrapolate. In other words, if it's built properly, it will also classify airplanes and cars it's never seen before. Okay, so that's the big question of what's called generalization in machine learning. And this is unbelievably successful, particularly in the last few years, for doing things like speech recognition, recognizing images, or even producing descriptions of images, recognizing faces, figuring out what a text talks about, translating languages from one language to another. And the history of this goes back to the 1950s. So there were, techniques in, essentially logistic, in regression and things like this in statistics, of course, that are kind of the ancestor of those methods. But really, what got people excited, at least for a while, is some work in the late 50s that was kind of derived from early work in cybernetics in the 50s, in a model called the perceptron. So perceptron is, you see a picture of it here down here at the bottom. It was actually an analog computer. It was sort of not a program on a regular computer. It was actually built physically. And it could be trained. It was one of the first systems that could be trained to kind of classify very simple shapes into two categories. And the basic module behind this was what's called a McCulloch-Pitts neuron, which basically is a very simple idealized model of neurons in the brain, where the learning takes place by changing coefficients that basically connect the output neuron with input neurons. They called it neuron, they're not neurons, but it's like we call the wing of an airplane with the same name as the wing of a bird, right? They don't have much to do with each other, but it's the same name. So what operation does this do? It computes a weighted sum of its inputs and compares it to a threshold. If it's above the threshold, the output is +1, category 1. If it's below the threshold, it's category 2. And the learning algorithm adjusts the weights so that you get, as often as possible, the output you want. So what happened is that, and there was a kind of similar effort at Stanford, Bernie Widrow here, working on the Adeline, which was a very similar model. So that was that sort of led to the dominant model of pattern recognition for the next 50 years, practically, where the way you build a pattern recognition system is you take the raw signal, let's say an image. So an image for a computer is basically an array of numbers, right? So the pixel values are just numbers, 3 numbers in the case of a color image, just 1 number for a grayscale. And then it goes into what's called a feature extractor, which is something that traditionally engineers had to build so that the system, this module here would extract the relevant features from the input signal, from the image or the sound or whatever it is that you want to recognize, into a vector, which is a list of numbers, and then the classifier, which is trainable, would be something like a perceptron, something that computes a weighted sum of those numbers, and the weights are trainable. Unfortunately, that model is very limited. For two reasons. First of all, those simple classifiers are limited in what they can do. They can't learn really complex concepts. And all the work goes into designing this feature extractor. So if you look at the literature in pattern recognition, speech recognition, computer vision, etc., from the early days to less than 10 years ago, all of it was about how do you design this, essentially. And you had to kind of do it again for every new problem you had to solve. So there's something that happened. The roots of that goes back 30 years, but the popularity of it kind of exploded only in the last 6 or 7 years, and it's the idea of deep learning. So deep learning is the idea that the way you build a learning machine is through you basically build it as a cascade of modules, but all of those modules have trainable parameters in them. And each of those modules computes a function that has some nonlinearity to it. And so by kind of stacking multiple nonlinear functions, if you make them kind of complex enough and the dimension of those vectors here is high enough, you can show that you can approximate functions as close as you want. But there's still the question of precisely what you're going to put in those boxes so that the system can learn complex functions of the inputs. And why is it that you need multiple layers? So the simplest answer to what you put in those boxes is basically what sort of constitutes an artificial neural network. So an artificial neural network is essentially a parameterized function that is composed of a sequence of two types of functions that are alternated. Okay, so the first one is, so imagine your signal is represented as a vector, just a list of numbers. You take this vector and, let's take this one, for example. This vector has components, each are those numbers. You compute a weighted sum of those numbers, and then you pass this weighted sum through a nonlinear function. Something very simple like this. That's the positive part. So it's a function that is the identity function if the argument is positive, and it's equal to 0 if the argument is negative. Very simple. And that's the output. So you have two types of modules, a linear module, which is basically just a bunch of weights. And the sort of operation here consists in taking this vector, multiplying it by this matrix, and then you pass the component of the resulting vector by those nonlinear functions. So very simple operations, multiplication, addition, and comparisons, and that's all you need to run a network like this. Now, you could have hundreds of millions, if not billions, of those weights in a typical system like this, and anywhere between 5 and 100 layers. Very early on, when people started working on neural nets, they were worried about the fact that the computers weren't powerful enough to run them. And so when I joined Bell Labs in the late 80s, what the group I joined was focused on is actually building chips to run those things fast. Not particularly those things, actually. It's sort of earlier ancestors, if you want, of those neural nets. And what you see here is sort of a history a little bit of some of those neural net chips. So this is kind of a very early one. This was constructed with electron beam lithography. You could build an array of resistors that could be used as a matrix, basically, and you can multiply voltages by this matrix and get a vector matrix product. Turns out, if it's not programmable, it's not very useful. So the next one was, programmable with binary weights, and then the next one was even more bigger and more programmable. This one had 32,000 binary connections, synapses, if you want. And then this one had kind of synapses that were represented on 6 bits, so a little more things, and it was a convolutional net accelerator. So the history of neural net is really intimately linked with hardware, and it's true again today. I'll come back to this in a minute. Okay, so from the sort of more mathematical or abstract point of view, if you want, the learning procedure really consists in sort of minimizing some function with respect to the parameters of the system, right? So you show an image, you run it through the machine, whose output is determined by those adjustable parameters, and then you measure the distance or discrepancy of some kind between the output that the machine produces and the output that you want, okay, which is also a list of numbers, some vector. So you can compute the distance between vectors in some ways, and what you want to do is find the setting of those parameters that will minimize this error averaged over a large number of training samples that you're going to train the machine on. Okay, so mathematically, it's an optimization problem, high-dimensional optimization problem, where the function you're trying to optimize, and we have optimization experts in this room, and the function you're trying to optimize is a sum of many terms, or an average of many terms, because this is the sum of all the contributions to the objective function of all the samples that you're training the machine on. So this is performed using something called stochastic gradient descent, which is a very simple algorithm that consists in showing an image, computing the output, measuring the objective function, and then figuring out the gradient vector of this objective function with respect to each of the parameters. So the gradient vector is basically the direction and magnitude in which you have to change those knobs so that the objective function goes down maximally for the smallest change. That's pretty much what it means. So what you do now is you change those knobs just a little bit so that the error goes down, and then you go to the next sample, do it again. And you do this thousands of times. So the mathematical concept to be able to compute this gradient vector, which is a vector the same size as the number of knobs that indicates the direction and magnitude of the change of the output with respect to each of those parameters. The way you compute this is through an incredibly sophisticated concept in mathematics called chain rule. First differentiation, second chain rule. The concept has existed since Newton and Leibniz, so nothing complicated there. I don't expect you to actually read those formulas unless you're really interested in. But what it comes down to basically is that if you have the gradient vector of which is how. So imagine you have a neural network which is sort of a cascade of parameterized modules like this that are stacked on top of each other that produce an output. If you know, so let's say you have the output of this particular module here, and somehow someone gives you the vector of gradients of the objective function you want to minimize with respect to this output vector, which is an output of the same size as this vector. To figure out the gradient of the cost function with respect to the input of that module, you just need to multiply this by the Jacobian of that box, and that's just an application of a chain rule to vector functions. That's mathematically very simple. There's another gradient that you want, which is the gradient of the objective function with respect to the parameters of the box that are kind of inside the box, if you want. And so what happens is that by propagating signals backwards, you can compute all the gradients. And the nice thing of this in terms of sort of software implementation is that you don't actually have to write the program to do this. The only program you have to write is a program that computes the output of your system as a function of the input. And using one of the pieces of software that people have designed, that I started designing in the 80s as well, you get what's called automatic differentiation. So you get the function that computes the gradient automatically. It kind of runs the tape backwards and kind of figures out how to compute the gradient automatically. So you don't have to do any math, basically. Okay, so the next question you can ask is, there's a slight problem with the model I showed you, which is that this one, which is that if you have an image might be several hundred pixels on the side. If you want the object to be recognizable, it might need to be 300 by 300 pixels or something like this, or 200 by 200 pixels, let's say. So that's 40,000 pixels. That means 120,000 variables because the pixels are color. So you get this vector with 120,000 components. You're going to multiply it by a matrix. Supposedly, you want a vector here that may be of a similar size, and that's going to be a very big matrix, 100,000 by 100,000. Probably not practical. So what you'd like is to constrain the type of matrix that you allow the system to use in such a way that they are kind of computationally tractable and they don't have too many parameters in them. And that's basically where this idea of convolutional networks comes from. So this is something I started working when I was still a postdoc in Toronto, and I really made it work when I joined Bell Labs in the late 80s. And the idea there is that you don't compute weighted sums for a particular layer where each unit in a particular layer is not connected to the entirety of the previous layer, to all the units in the previous layer, but it's only connected to kind of a small patch with a set of coefficients. And what's more, the coefficients are going to be the same for all the units in one of those maps. So you see a whole network here being represented. That's the input. The first layer consists of 4 so-called feature maps. And the way you compute each of those feature maps is that you take a patch from the image, you compute a weighted sum of the pixels in this patch with a set of coefficients, and that gives you one value here. And then you take those set of coefficients, you swipe it over the entire image, and you record the resulting weighted sums. This operation is a discrete convolution, hence the name convolutional network. And then you pass the result through this pointwise nonlinearity. In this case, it's a hyperbolic tangent, but it could be something else. And that's the first layer of a convolutional net. The second layer does what's called pooling, which consists in aggregating the response of the filters in a small area, and kind of stepping this region over which you aggregate by more than one pixel. So what you get is a sort of lower resolution version of this image after the pooling operation. The reason for doing this is to build a little bit of invariance to shift and distortions in the system. And you can see this here in this demo. So this is a convolutional net in action, kind of a vintage, early 1990s. It's been trained to recognize handwritten digits, and this is the first layer. The second layer after pooling. The third layer also does convolutions, and this one performs convolutions on each of those maps with different sets of coefficients. The coefficients are learned, I should say. These are what is learned by the gradient descent algorithm. So the result of the convolutions are added together, and then the result is passed through nonlinearity. So what those maps are doing is that they are detecting combinations of features appearing on the previous layer. And then pool again, and subsample, and then do convolutions again. So as you go up the layers, the representation of the image becomes more and more abstract, but more and more global. So every pixel here, every value here is influenced by essentially the entirety of the input. And so this worked really well for recognizing things like characters. And back in the 80s, we didn't have the computers or the data sets to do anything else on recognizing characters. There was basically no other problems for which you could collect enough data to train a system like this. And it was maybe for speech recognition, but it didn't quite work at the time because our networks were too small. We figured out pretty quickly that we could actually not just recognize single characters, but also multiple characters with a single convolutional net by kind of swiping it over the input, which we could do extremely cheaply. So that's why I kind of drove people at the lab in Bell Labs where I was working to kind of work on hardware, because perhaps there were practical applications that could be deployed. So practical applications were deployed, as Leslie mentioned, for recognizing checks, in the mid-90s, and by the end of the 90s, they were reading something like 10 to 20% of all checks. We don't exactly know the exact number. By that time, by the mid-90s, the entire machine learning community lost interest in neural nets. And by the late 90s, you could not actually publish a paper in a machine learning conference that spoke about neural nets because they had the reputation of not working, despite the fact that they actually were working. And the reason was that this was, the mid-90s. This was before the internet, really, and so there was no way. And this was before, companies were ready to kind of distribute their code, and this was before there were kind of standardized computing platforms and things like Python and things like that. And so it was impossible for people to reproduce those results, basically, and we could not distribute our code easily, or if we did, people didn't want to use it. So, so there were a lot of tricks to kind of make those things work. And it was just too complicated for people to reproduce, so it was basically abandoned with the excuse that it didn't work, but it did work. So I actually stopped working on machine learning for a few years, worked on this déjà vu project that Leslie was mentioning, and came back to it a couple of years before I joined NYU and started working on projects like robotics. So we figured that because those convolutional nets could be used to detect objects by swiping their input over an image, we could use them perhaps to drive robots. So this was a project that I worked on at NYU in collaboration with a small company in New Jersey called Nescale Technologies. And this is the result, if you want, of applying the neural net to an image where the three categories that we train the neural net on is whether a piece of ground is traversable or whether it's an obstacle. And the neural net sees kind of a small region, if you want, of the image to be able to make that decision. And this is done by a convolutional net that is run over the entire image. So we can collect the labeling for this. We don't have to actually label those things by hand, because for objects that are nearby, using stereo vision, we can figure out if something sticks out of the ground or not automatically. It doesn't work in the long range, but it works for nearby objects. And so we kind of trained this robot system, and this is the architecture of the neural net, the convolutional net that was used for it. and you place the, so you get those segmentation, it's called semantic segmentation of images, and you can sort of put the corresponding labels in a map, and then use this map, this traversability map, if you want, with a planning algorithm to figure out, how a robot can go to a particular goal. The system also has another kind of faster vision subsystem to avoid unexpected obstacles that jump in front of it, because the neural net-based system only runs at about 1 frame per second. And that worked pretty well. So this was done around 2008. I think this video was from around 2007, 2008. These are the two students who worked on it. They both work at Google. This is Raya Hetzel here, leads the robotics research effort at DeepMind. Pierre Samanet is at Google Brain in California. They're pretty confident they can jump in front of the robot without their legs being broken, because they actually wrote the code. And they trained the system. So this is kind of the next step. So a couple of years later, working with another student, some data sets appeared that basically labeled every pixel in an image with the category of the object it belongs to. And so we trained a convolutional net to do this task. It was far from perfect, but at the time it beat all the records on this particular data sets. In fact, on 3 different data sets of this kind. This is the middle of Washington Square Park. I mean, we're getting into Washington Square Park, and it's labeling those kind of bright area as sand or desert or beach. This is middle Manhattan. There's no desert I'm aware of, but it worked as well as it could. So we wrote a paper that we submitted to one of the leading computer vision conference, because not only did we have the best performance with the system, we also had the fastest system by a factor of 50. And the paper was rejected by all 3 reviewers, who said, basically, what the hell is a convolutional net? We don't believe that a method we never heard of could work so well, so basically it's wrong. So the funny thing, this was 2011, and the funny thing is, 4 years later, you could not get a paper accepted at the same conference unless you use convolutional nets. Okay, so that gives you an indication of the revolution that occurred in just that short period afterwards, which I'm going to come to in a minute. That gave some ideas to a bunch of different companies like NVIDIA and a company called Mobileye, which was an Israeli startup at the time, which was recently acquired by Intel. And they kind of used this idea of semantic segmentation to kind of allow a car to drive itself. And they were one of the instigators, if you want, of the big wave of interest in autonomous driving. And NVIDIA is working on it. In fact, the people at NVIDIA who are working on, some of the people at NVIDIA who are working on this are the same people who collaborated with us on this robotics project that I was telling you earlier. So deep learning today is absolutely everywhere, in the sense that convolutional nets and various other models of this type are used very, very widely by companies like Google, Facebook, etc., all the online services, to the extent that if you took out deep learning today from those companies, they would basically crumble. I mean, everything is built around them. So what happened was the revolution really occurred around 2013, 2012, 2013, when the so-called ImageNet competition, which is a competition for object recognition in images, was won by our friends at University of Toronto, Jeffrey Hinton's group, where I had done my postdoc many years before. And they were really good at sort of implementing those convolutional nets on the very fast GPU cards. So GPUs are those kind of cheap, relatively cheap cards that are designed for graphic rendering. They're basically designed for gamers. So it's very low cost, but they are capable at the time, they're capable of about 1 trillion operations per second for a card that you buy for a few hundred dollars. So it gives you a supercomputer for very cheap. And so they were really good at implementing those convolutional nets. They were not the first one to do it, but they were really good at it, implementing those convolutional nets on those GPU cards. And with that allowed them to train a very large convolutional net, much larger than was ever possible before. The ImageNet data set was quite large, with about 1 million training samples, 1.3 million training samples, and they just completely blew all the results out of the water. So in 2011, the best error rate on this data set was a little less than 26% error, and they got it down to 16%. And then the next year, there were another couple of convolutional nets, including one from my group at NYU, that got this down to about between 10 and 12%, and then it was 7, and then 6, and then 3, and then 2, and now it's not interesting anymore because it's better than human performance on this data set. And what's happened simultaneously with this is that the number of layers in those networks kind of kept increasing, ballooning is really. So things like this, where those networks now that are routinely used in production at Facebook, Google, etc., have 50 layers or so. This is a slide that was put together by someone who's now a postdoc in my lab, Alfredo Canziani, where this represents the accuracy on this ImageNet dataset and the billion operations per second that are necessary, the billion operations, I should say, that are necessary to compute one output of one of those neural nets. And people sort of made progress in sort of making those networks smaller while making their accuracy better, right? So the state of the art here, is kind of around here right now. That's where the production systems are used. So one question we might ask is, why is it that we need multiple layers? So if you ask a mathematician, how can I approximate functions with the type of elements that I showed, there would be theorems that go back to the late 80s that say you only need 2 layers. One layer with a linear operation, one layer of nonlinearities, and it doesn't matter what they are, and then another layer of linear combination. And then if you have enough big enough high enough dimension in the middle, you can approximate any function you want as close as you want. There's no limit on the dimension of the middle layer. But what happened is there's a lot of functions that are much more efficiently represented if you have multiple layers. So it's due to the sort of intrinsic kind of sequential nature of the computation that requires to be done, but also something much more intuitive, which is the fact that having a network with multiple layers allows the system to learn representations of the perceptual world that is hierarchical, right? So why is it good to have hierarchical representations of the visual world? It's because the visual world is compositional. Images are formed by pixels, and then local motifs like edges, oriented edges, are formed by particular combinations of pixels. And then you assemble those motifs into slightly more complex motifs like corners and crosses and things like this, right? And then those assemble to form parts of objects, those assemble to form objects. So you have this sort of natural compositional hierarchy in the perceptual world because the world is compositional. And we might ask, why is the world compositional? It might be a conspiracy. That's what makes the world understandable to us, for the same reason. So there is actually an inspiration of those convolutional network architecture from biology. The original inspiration for that comes from classic work by Hubel and Wiesel in the 50s and 60s, Nobel Prize winning work in the sort of neuroscience of the neurophysiology of the visual cortex, where the equivalent of this convolution, what they call simple cells, and the equivalent of those pooling operations that I described, they call them complex cells, and those things were identified in the visual cortex. So the idea of sort of putting this together into multi-layer systems that you can train was originally done by a gentleman by the name of Kunuhiko Fukushima in Japan, but he didn't have the backpropagation learning algorithm, so he had kind of trouble training it properly, and so backprop enabled really the performance that we see today there. So modern computer vision, actually using convolutional net, has made a lot of progress in just a few years since those first experiments. Those experiments with ImageNet, where the system could basically just tell you the name of the dominant object in the image, and then just a couple of years later, there was kind of networks that were able to produce masks of each of the objects, and then maybe describe produce a description of the image. I'm not going to bore you with details of how this is built, but it's conceptually very simple. It's just a convolutional net, or some combination of convolutional net with sort of multiple resolutions, etc. And what those things can do is basically produce images like this, where you show them an image, and then they give you a mask for every object in the image, every instance of every object in the image, every category, together with a score. And it can pick out small objects in the background, wine glasses, etc. This runs really fast. It can be run at multiple frames per second, if not more. You can get those machines to count sheep and recognize elephants and stuff like that. But the problem is that they still require a lot of samples to be trained. Thousands, if not millions, thousands per category. This is an example of a demo system. This actually runs at that speed on an iPhone. So it's a system that uses convolutional nets to identify key points on human bodies and that reconstructs the pose of the human body. And this runs in real time on a smartphone. So what you're going to see over the next few years is that there's a lot of demand for potential applications of those things on mobile devices and also like augmented reality glasses and things like this. And what's missing are low power, low cost chips that can run those neural nets really fast. You're going to see those things popping up in your smartphone, over the next few years, and they're going to be everywhere. Not just in your smartphone, but also in your vacuum cleaner, in your automated lawnmower that can avoid the flower beds and things like that. And this is all. So this is work by my colleagues at Facebook AI Research, and it's all open source, which means you can download it and play with it. This is another system also produced at Facebook. This one in Paris for pose estimation, but it's called dense pose because you can identify a lot of key points on people. This runs in real time on a single GPU. This demo, and you can substitute the clothing by some other, etc. More seriously, though, there are applications of this that I think are going to have a big impact on society. Of course, in autonomous driving and transportation, road security and stuff like road safety, but also in medical imaging. That's one of the hardest topics in medical imaging these days is the use of deep learning for radiology, essentially. So this is a particular type of convolutional net called the UNet architecture. And it was produced by some of my colleagues at NYU to sort of segment the images of femur for, I guess it's for hip replacement surgery, I would imagine. This was a recent paper in Nature, where the system does a really good job at doing this. So I've talked about computer vision and pixels, but convolutional nets also can be used for things like translation. I'm not going to go into details, but for a while this is what Facebook used. It can be used for sound and speech recognition, but also for sound generation. This is some recent work from a few students at Facebook in Paris that use a funny kind of reverse convolutional net to synthesize musical sounds, or reproduce musical instruments that are parameterizable. So this is a completely different application here. This is not, well, there is a little bit of convolutional net involved there, but they are very simplified in some ways. But it's for producing embeddings of text, particularly words in text, and automatically translating text from one language to another without ever having seen parallel text of the two languages. So the idea behind this is kind of cute. You train a system to on a large corpus of text from one language, and you train it to predict one word from the surrounding words or from the preceding words. Okay, so you take a segment of words, you mask out some of the words, and you ask the system, tell me what words are missing. And in the process of doing this, the system has to map every word to a vector in such a way that the vector contains the information that will allow it to produce the answer. So what you get at the end of the training procedure is that you get a vector associated with every word. You do this for two languages, and what you get now is that a language is represented by a point cloud, a cloud of vectors, right? Now, turns out human languages have a lot in common, and so the next step is to try to find a simple transformation, let's say an affine transformation, from one of the point clouds to the other one, so that the shapes match, more or less. And if you do this, what you get automatically is a dictionary. It's amazing that it works, but it does. And it's actually used by Facebook because people use something like 5,000 languages on Facebook, and we don't have enough data to translate every 5,000 into every other 5,000, right? Right, so a lot of applications of deep learning in medicine, in transportation, in science, high-energy physics, chemistry now, a lot of people doing this. And in chemistry and other data set, or the type of data, there's a very interesting generalization that has appeared over the last few years, which is deep learning applied to graph data. So instead of, you can think of an image as a function on a regular graph, a grid, right? But there is a lot of data that comes to us not in that form. They're not in the form of a multidimensional array. They're in the form of values on a graph, for example. Let's An example of this is chemical formula, right? So a molecule, you can think of it as a graph, and it's a function on a graph that represents the identity of the atom at each site. Another example of graph is a 3D mesh, so a 3D mesh that represents a 3D object, or a graph of interactions of genes, for example, or regions of the brain. And the question is there an equivalent to convolutions for data that comes to you on an irregular graph? And for the mathematicians in the audience, will not be surprised to hear, because they already know it, that you can actually define something like convolutions on irregular graphs, because a convolution is a diagonal operator in the Fourier space, and you can define Fourier transforms in irregular graph. It's a transformation into the eigenspace of the graph Laplacian. I'm not going to explain what that means for people who don't know what those things are, but basically you can define convolutions on irregular graphs, and that means you can run neural nets on things that come to you in a funny form. And there's a lot of potential applications of this. It's a very sort of early stage, but it's really interesting. So another form of learning besides supervised learning that has people kind of excited in the last few years is something called reinforcement learning. So reinforcement learning is a scenario in which, or paradigm in which you don't tell the system, here is the answer you should produce. The system sort of produces an output and then gets feedback as to whether the output was correct or not. Just a scalar value, okay? And the problem with this is that the objective function that computes this thing is not differentiable. You don't know it. It's basically the environment that tells you you did good, you did bad. And so the system cannot differentiate the environment, so it has to sort of do trial and errors. Okay, so that works really well for training a machine to play games. Like if you want to train a machine to, beat humans at Doom or beat humans at Go, or more recently at StarCraft, you can actually use those systems. Basically, you have a system playing millions of games against itself, and then figuring out what's the best strategy to kind of beat itself, and then sort of compiling that knowledge into a neural net, essentially a convolutional net. In the case of Go, what AlphaGo, built by our friends at DeepMind, Google DeepMind, did was basically plug a convolutional net looking at the Go board, and then training this convolutional net to predict what is the best move that I should do at this point. Okay, trained initially with imitation learning and then reinforcement learning. The more recent version is completely reinforcement. This was a bit of a shock for a lot of people that you could, train a machine to beat people at Go. It was a bit of a Sputnik moment in China, where Go is sort of a, quasi religion, and so that kind of prompted a lot of people in China to kind of get interested in those things, because they were kind of like the US got into the space race because of Sputnik. So there's a problem, though, with reinforcement learning, which is that it's horribly inefficient in terms of trials. So here is a bunch of curves of the learning curves from a paper from DeepMind, where they train a system to play classic Atari games, and they measure the performance, and they measure how long it takes for a system to reach roughly the performance of a human, playing casually. And the bottom line is that it takes, on the order of 80 hours or so, on average, for those systems to learn to play those games at the level where that a human can attain in about 15 minutes of play. So obviously there is something that humans, do that those machines don't do. Learning so efficiently with so few exposure. And that's a big problem in practice, because you'd like to be able to use those learning algorithms to get a machine to, for example, drive a car by itself. And it will have to, run off a cliff a few tens of thousands of times before it figures out how to not run off a cliff. And, kill a few million pedestrians and, crash into a few million trees. So that's just not practical, even in simulation. So what is it that allows most humans to learn to drive a car in about 20 hours of training without crashing? That's the big question. What are we missing to get to real AI? So in my opinion, this is a very personal opinion, not everybody agrees, but I think we need three things. I'm I'm only going to talk about number 2, really. Number 1, I'm going to go very, very quickly on it. The systems I've described, they can all do perception. There's 2 things they cannot do. They cannot do reasoning, and they cannot do actions, or at least they cannot plan complex sequences of actions. Okay, so those are 2 things that we're missing. But what we're missing also is the ability for the system to kind of learn models of the world. So what allows us to learn to drive a car so efficiently with only a few tens of hours of training is the fact that we have a good model in our head of what will happen if we turn the wheel and there is a cliff and the car runs off the cliff. We don't need to actually do it to figure out what's going to happen. Okay? So we have this predictive model. How do we get those machines to learn those predictive models that, will keep them out of trouble? And it's a very important question, because what we want to do with those AI systems is not just, better medical image analysis and stupid chatbots and stuff like that, and Alexa and Siri, where you can ask them like 10 types of questions, and if you go outside of those 10 types, they really can't help you. What we'd like is machines that have a little bit of common sense, that they understand what you're talking about. They have some deep understanding of what you're talking about, because that's necessary for building things like intelligent personal assistant. And a lot of those big tech companies, that's what they want to build, right? They think that's where the big thing is in the future. We also want household robots. They've been promised to us for decades, but they still don't exist. And the main reason is not that we can build the mechanics of it. It's just that we can't make them smart enough. Or smartest robots have less common sense than a house cat. So I would consider it a success in my career if, by the end of my career, which is coming fast, we have a machine that has as much common sense as a house cat. I used to say a rat, but I've sort of upped the okay, so for reasoning, there is a set of ideas that I'm going to go extremely quickly on, which is the idea of differentiable programming. So it's the idea really that a neural net will not have a fixed architecture, but it will basically be the result of a program, and that the structure of the neural net will be data dependent. So it depends on what data it's looking at. And I'm just going to give you a very simple example of some work that was done at Facebook recently in this direction, where you show an image like this to a machine and you tell it this text. There is a shiny object that is right of the gray metallic cylinder. Does it have the same size as a large rubber sphere? And you kind of have to think about it, right, to answer this question. You kind of have to configure your visual system to detect the relevant objects and then compare their locations, blah, blah, blah. And so that's exactly what this network does. It analyzes the sentence. It basically turns it into a sequence of vectors. And then the output of that network is itself a neural network that is specifically designed to answer that question. So it basically has a rubber sphere detector and then a gray metallic cylinder detector, and then it figures out the relative position of the two, and it figures out if it's shiny, and then compare the size, and then answers yes or no. And so if you put those modules in the right order at the right place, according to this question, you'll be able to answer the question. And the beauty of this system is that you can train it end-to-end using something like gradient descent algorithms with a few tricks, and it works. So that might be a path towards machines that can reason, not just perceive. But it's still very preliminary. And this might lead to a new way of writing software, right? So the way you design those networks is basically you write a program, and the output of the program is the output of the network, but the piece of the program that are executed depend on the input data. And so it's not a fixed architecture network. And you can think of this as a program whose functions, whose calls, instructions are not completely determined at programming time. Their individual functions are basically learned from data, okay? And some people have called this software 2.0, differentiable programming. Basically it's kind of a new way of writing software, if you want, that uses machine learning. Okay, so how do humans and animals learn? What allows them to learn so fast? So there is a bunch of really basic things that we take for granted, but that we actually learn at an early age. We learn a huge amount of background knowledge about the world in the first few weeks and months of life. So for example, if you show a baby younger than 6 months old, this kind of scenario where there's a little car on a platform, you push the car off and it floats in the air. It's a trick, of course. Baby 6 months old, they barely pay attention to it. They say, sure, that's how the world works, no problem. After 8 or 9 months, they figured out that objects are not supposed to float in the air. They're supposed to fall, right? There's gravity, right? And they go like this. So, and you can measure this, okay? So if you are a developmental psychologist, you can actually measure the degree of surprise and figure out if babies have learned a particular concept or not. And that's, that's the story here. So you get, this is a chart that was put together by Emmanuel Dupuy, and this is the number of months at which babies learn sort of basic concepts like object permanence, for example, that an object is still there even if it's hidden, things like that. And then gravity, inertia, conservation of momentum, that happens around 7 or 8 months. So how do we learn all that stuff? Babies are helpless in terms of action, so they mostly learn this by observation. And it's not just babies, it's animals. Here is a baby orangutan here, and he's played a magic trick. Put an object in a cup, shake the cup, remove the object without the orangutan seeing, and then the cup is empty, and the orangutan was on the floor laughing. And that's because his model of the world, is violated, right? And so when your model of the world is violated, you can laugh. Okay, that's a good trick for humor. Usually you pay attention. Sometimes you get scared because here is something that happened you didn't predict, right? So it might be dangerous. So the future, I think, is something I call self-supervised learning, which is the idea that you can train a machine to learn how the world works just by observation, by exposing it to a lot of different segments of data. So a good example of this, so let's imagine for the sake of concreteness that you show the system a piece of data. Let's say it's a video. Okay, so this is time here going this way, and then you have video frames. You can ask the system to predict the future from the past. You can pretend you don't know the future. Just wait a little bit and you will know it. So you can train the machine to predict the future from the past, or from just the present, or predict the past from the present, or predict the top of the image from the bottom. I mean, there's a lot of different ways that you can ask the machine to sort of complete sort of an incomplete piece of information. So it's called self-supervised because you don't provide labels or outputs to the machine. You're basically training it to predict part of its inputs. Okay. And so it's the idea of prediction and completion. And the reason why I think this might be the ticket to machines with sort of some level of common sense is that if you think about how much feedback you give the machine in the context of reinforcement learning, it's a very weak feedback. You tell the machine you're right or wrong once in a while, and it's just a single scalar value. It's not much information there. For supervised learning, you tell the machine this is a car, an airplane, or whatever. You have 1,000 categories. That's just 10 bits of information per image. Not that much. But if you ask the system to predict what's going to happen in this video, it's going to have to predict a lot of stuff. And therefore, it's going to have to kind of acquire a lot of background knowledge to be able to figure out how to predict this video. It's going to have to figure out that there are objects in the world. There are objects that can move, and others that move ballistically, and some that move voluntarily, etc. So that led me to this slightly obnoxious picture, or analogy, which is that if intelligence, the quantity of stuff that you learn, if you want, with different paradigm, if you kind of assimilate this to a cake, the bulk of what you learn is through this kind of self-supervised learning paradigm. You learn a little bit through supervised learning, where you're being told the name of things. We'll show you a picture book, and I'm telling you this is an elephant. And then reinforcement learning, where you learn by trial and error. That's just a tiny piece that you can learn because the feedback is so bad. You need, it's very inefficient. You need a lot of trials to learn anything. So people who work on reinforcement learning get slightly upset when I show this, and some of them work at Facebook. So this doesn't mean that reinforcement learning is a bad idea. It means that if I give you a cake, which is just a cherry without the cake itself, I don't think you'll be very happy. So we need to work on the cake before we can basically use the cherry in a good way. Basically self-supervised learning is the idea of learning by learning to fill in the blanks. And there's a lot of work in computer vision in that direction, where you block out a piece of a picture and you ask the machine reconstruct, and there's kind of good progress there over the last few years of kind of dreaming up the piece of an image that has been blocked out. It's been extremely successful in the context of text. This is a model called Bert. There's one called Bert, there's another one called Elmo. I mean, they have characters from Sesame Street for some reason. I'm not sure. It's actually an acronym. But this is from Google, and it consists in sort of learning representations of text by showing a piece of text and then masking some of the words and asking the system to predict those words that are missing. And so, it has to kind of have some good idea of what the underlying representation of things is. But there's a big problem with this, which is that you cannot exactly predict which word is gonna go here. It could be a number of different words. And so you cannot ask the machine to make one single prediction. You have to ask it to predict the distribution over words. That's possible in the case of text because the dictionary is finite. It's 100,000 words or so, and so we can compute the distribution over 100,000 items. It's a bunch of numbers that sum to 1. Between 0 and 1, that sum to 1. That's easy enough for a computer. So that works great for text. It doesn't work for things like video prediction. And the reason it doesn't is because we actually don't know how to represent useful probability distributions over sort of high-dimensional continuous spaces like images. Right? So if you train a system to predict what's going to happen in a video by just using, minimizing the squared error between what happens and what the machine predicts, you get blurry predictions. And the reason for that is simple to understand. Let's say I do an experiment where I put a pen on the table and I let it go, and I always put it in the same place and I always let it go. And you can predict that the pen is going to fall, but it's probably going to fall in a different direction every time I do it, and you're not going to be able to predict in which direction. So if I ask you to make one prediction that sort of minimizes the error with all the events that can occur, what you're going to have to predict is basically a transparent pen in all possible configurations, right? Which is not a good prediction. And that's exactly what happens here. You get a transparent girl, which is the average of all the possible girls, basically, or future girls. So I think this is going to be the next revolution in AI, and the next revolution in AI will not be supervised. Maybe televised, but not supervised. I'm just going to give you one example of how this works in sort of a practical situation. Why we would need to predict, to learn predictive models of the world, why we need machines to learn predictive models of the world, and how they can help with problems I was mentioning before, like getting a car to learn to drive itself. So one thing that has been sort of a classical way of proceeding in optimal control is that if you want to figure out, compute the control, the sequence of controls to shoot a rocket and meet the space station. The classical way of doing this is that you have a mathematical model of the rocket, which, given the state of the rocket at time t, predicts the state at time t+1, given the command that you give it, okay, thrust and orientations, whatever. So you can run this model for minutes, and then figure out you have an objective, which might be the, amount of fuel consumed, the total time it takes, and the distance to the space station at the end. And what you do is, by gradient descent or some other mechanism, you find the sequence of commands that will minimize this objective. Okay? And this is very classical, going back to the 60s. So the problem is, we don't know in advance what our situation where a robot or a system is going to face a particular situation. We need to have a predictive model of what can happen. And if we had that, then we could have intelligent agents that, basically could simulate in your head, in their head, what's going to happen, and then figure out a plan of action that will result into a good outcome. So that's kind of the idea of learning world models. And you can learn world models because, let's say you're trying to train a car to drive itself. You have the state of the car at time 0, perhaps with the complete environment surrounding the car. You have the action that you can take at one time. You can predict the next state of the car. And then this next state, you might minimize the error with, between the prediction of the next state and the state that actually occurs. And then, train your forward model to basically do a good prediction at what's going to happen. In the context of optimal control, that's called system identification. Let me skip ahead a little bit. I'm not going to talk about adversarial training. Actually, let me talk a little bit about adversarial training very quickly in just 1 minute. So if we go back to the scenario I was talking about here, where there are sort of multiple possible future predictions for a sort of initial segment of a video, let's say, what I need is a function that does not produce a single output, but a function that produces a whole range of outputs, depending on variables that I cannot observe, like exactly where I lifted and how I lifted my finger. So I'm not going to be able to predict exactly in which direction the pen is going to fall, but what I could do is basically feed to this deterministic function a set of so-called latent variables, which are variables I don't have access to. I don't know what their value is. I might draw them at random with some distribution. But the idea of it is that as those variables vary within a set, then the output varies within the set of plausible futures. Okay? That's called a latent variable model. There's one way to train a system like this, which is to draw this variable at random, and then train the system with a cost function that tells this neural net whether the prediction that it produced is on this set of plausible futures or outside of it. Okay? The problem is that we don't know what this set is, so we're going to have to train a second neural net to tell us whether we're on the set of possible futures or not. And that's the idea of adversarial training. So it was first proposed by Ian Goodfellow and Yoshua Bengio and a bunch of people at the University of Montreal a few years ago. In my opinion, probably the most interesting idea in machine learning over the last 10 years, if not 20. And so you take an initial segment of a video, and you know how the video continues. That's the real data. You run this through a function that is going to be the one that computes whether you are on this set of, let's call it a manifold, it's not a manifold, this manifold of possible futures. And so you train this discriminator to produce a small output, a low output, when it sees stuff that actually occurs. And then you take your other neural net, the generator, using sort of randomly sampled latent variables to make a prediction for what's going to happen. Initially, it's going to be terrible. You train the discriminator to tell you this is terrible, and you do this by training it to produce a high output. Okay? So what happens after a while is that the discriminator learns to tell the difference between plausible futures that have kind of a low output of the discriminator and bad predictions that have a higher output. Okay? And they are the ones that are produced by this guy. Now, the next thing that happens is that through backpropagation, you can figure out the gradient of the output of the discriminator with respect to the parameters of the generator, and so the generator can be trained to produce an output that the discriminator cannot tell is fake. All right? And so what you get in the end is that those green points that are generated by the generator end up, near the points that are the real things, but what you have now is kind of a distribution of those green points that is similar to the distribution of blue points. And people have been using this. I mean, it's been incredibly successful for doing things like generating spontaneous images. So here, this is an example where there is no conditioning on the past. The only input to the neural net is a bunch of random numbers, and out comes the image of a face, 1,000 by 1,000 pixels. It's been trained on a bunch of faces of celebrities, and those are non-existing celebrities. Okay, they belong to the same manifold as the celebrities the system has been trained on, whatever that means. Okay, but it looked pretty good. So this was work done by people at NVIDIA in Finland. At Facebook in Paris, we've been working on a similar project, and because it's Paris, it's not faces, it's clothing. So we've been working actually with a big kind of designer house, and they gave us tons of data, and we trained a generative model on the data, and then we let the system basically create pieces of clothing, and that's what it comes up with. And you wouldn't imagine a human designer kind of coming up with this kind of stuff. So you show this to the designers, and either they like it and they use it, or they say, well, that's a good idea. That sort of gives me an inspiration. And I think you're going to see a lot of use of those systems in the future for creative, creative aids, basically. So video prediction, I mentioned that. We can use those systems for video prediction, but let me skip ahead a little bit. One thing you can do with video prediction is predict what the cars around you are going to do. So here's let me show you just a little demo of this. I'm looking for the appropriate video here. Okay, here's one. So this is a system that does not predict pixels. It predicts those maps of kind of segmented objects, if you want. So the vision system I talked about earlier, which produces those maps of objects. You can run this on images, and then you can train a system to make predictions in that space. And so it predicts that as the car moves, the cars on the side are going to have to kind of move back. The scenery is going to have to move, and then the cars in front of you. So it's kind of predicting, that it's moving in the right direction, but it's not doing a complete, exact prediction. The car kind of shifts up a little bit. It kind of, does a decent job, and it's a very good idea to be able to predict what the cars around you are going to do when you drive. So these are other examples. So here, this car is accelerating, and the model doesn't predict that the car is accelerating, so the mass kind of trails behind. But here is a slightly more interesting model, or interesting direct application for self-driving. So let's say we have a bunch of cameras looking down at a highway, and we kind of collect data, and we turn it into something like this, where every car is a little rectangle, essentially, or bus. And the lanes are represented red here. And then we take every car, and we extract a little rectangle of kind of surroundings of that car, where the car in the center is just horizontal. And then we train a predicting system from a few frames of the surrounding of a particular car. We train a system to predict what this surrounding of the car is going to do. Okay, and again, it's not completely predictable, so there is some uncertainty in this. So we have to use one of those models with latent variables, whose details I'm not going to go into. And the kind of predictions that we get look like this. So this is sort of what happens in the real world. You initialize the system with the same starting position, and then you let it run. And for two different drawings of the latent variable, you get two different futures. And this is if you don't have a latent variable. So if you insist that the system make a deterministic prediction, you get sort of blurry mess. Okay, well, which is the same issue I mentioned earlier. So that's good. You can compute a cost function for how well this car is driving by basically computing how far it is from its neighbors and whether it's in lane and is driving in the right place. And then you can simulate a whole system where here is an initial state of the world around me, an action I'm going to take, I'm going to turn the wheel, accelerate. Here is the next state of the world. Here's the cost I can predict for that new position of the world, and I can run this thing multiple seconds in the future, and then through gradient descent, figure out how to train a neural net here to take the action that will minimize the cost. So basically, I'm training here a car to figure out how to drive, and the only thing the car is doing is thinking in its head what can happen around it. It's been observing what can happen around it through those cameras. So it's never interacted with the real world, okay? And you let it drive, and it doesn't work very well. It doesn't work very well because it goes into regions where the predictive model does a terrible job very quickly. And those are regions that happen to have a low cost where the prediction model doesn't work. And so you have to add another term in the cost that indicates whether the predictive model is sure of its prediction or not, okay? Whether it's reliable or not. And if you add that term, it works really well. You get things like this. So this is the car driving itself. And you have to realize it's driving in a traffic that doesn't see it. So it's like you're driving an invisible car, right? The other cars don't see it because those are real cars. This is recorded video. And this guy is trying to kind of avoid, being bumped into, essentially. And sometimes he gets squeezed. But, it sort of works. So here is my last slide. And I'm slightly over time. Very often we have, there's a lot of theoreticians in the room, and very often we like to think that, theory kind of suggests what, sort of precedes the practice. And it happens. But very often in the history of technology, it's kind of the other way around. People invent artifacts, and then they come up with a theory that explains it. And that theory sometimes end up being extremely fundamental. So things like thermodynamics was basically invented to explain the steam engine. But it became kind of the foundation of all physics, essentially, right? Optics was invented to explain the telescope and the lens and things like this. Aerodynamics existed before the invention of the airplane, but it was really refined for that. Computer science, of course, followed the invention of calculators, and obviously information theory followed the invention of communication technology. So all of those are very basic techniques now that we use every day that are very useful in the modern world. And the question I'm asking, and which is kind of my scientific project really, is there something like that for intelligence that explains intelligence? The equivalent of aerodynamics or thermodynamics, but for intelligence. And it would be nice if that was the case. So I'm not thinking about something that is reduced to 3 equations, but some underlying principle, right? And that could explain both artificial and natural intelligence. And that's my project for the next few years until my brain turns into mush. Thank you very much.